Hello there, friends. It's Ben again, and I am here with yet another of my mind-blowing videos on differential calculus. Today's video is about taking derivatives of logarithms and exponential functions. We've already been doing that with e to the x. Now we're going to look at doing it with all the other possible bases, as well as then the inverse functions, their logarithms. We already saw a little bit about this the other day, and I'm going to have a quick reminder on that. And then we're going to go on and see what all you can do with these. So, all right. Bear with me here because I had some problems with iPad stuff earlier. So hopefully, wow, a bunch of options vanished on me. Huh. Okay, let's see how this goes. Yay, it's going to work. All right. So we are taking the derivative of the natural logarithm function, and we have to remind ourselves over to the side that the logarithm function is just designed to undo what the exponential does. And because of that, when you take and compose the two functions, either order, you should get x out of it. Now, of course, when we're saying that sort of thing here on this one, we have to keep in mind the domain of the logarithm function. If you look at a graph of it, you can only have x values that are greater than 0, okay? And that is compatible then with the exponential function has a range of numbers that are greater than 0. There's no way to get an exponential that will give you 0 or anything less. So consequently, there's a little bit of restriction there, but our essential idea is that these functions are inverses of each other. Because of that fact, you can go ahead and write down that e to the ln x will be x. And if we differentiate both sides of that, and we know what the derivative of plain old x is, and that just gives us 1. But with the left-hand side, we have to remember that the derivative of an exponential is just that thing, but that the chain rule says we have to take the derivative of the thing that was in the exponent. So this means that the derivative of log x is 1 over e to the ln x. And we could just leave it like that unless we happen to know that special property that those are inverse functions and they just undo each other. So that gets us that 1 over x is the derivative of your log x. Let's see if I can put a little rectangle around this, make it look all fancy. Fancy-ish. Okay. So with that in mind, we're going to now go ahead and show that the derivative of any logarithm has a relatively nice formula, okay? So you might think that the natural thing for us to do here is to say something about b to the log base b of x is equal to x, or that the log base b of b to the x is x, because again, those are inverse functions of each other. And that's the way we accomplished this with the other one. But it's actually going to be more convenient here for us to notice this. E to the, e to the ln b is going to be b, right? So if we've got b to the x, we can rewrite that as e to the ln b to the x. And so we have e to the x ln of b. Okay, keep that in mind. It will crop up later on there. But the thing that really lets us do is something that came up from a pre-calc class, that whenever you want to take the log base b of something, if you don't have a log base b button on your calculator, then you can go ahead and just divide the ln of x by the ln of b. Okay, so yeah, referred to as a change of base formula. So if you know that, then when we transfer that up here, you can take the derivative with respect to x of the log base b of x, and that means to just take the derivative with respect to x of ln x over ln b, but the ln b is just a constant, so we're allowed to factor it out. And so then you still have to take the derivative of ln x, but we did that on the previous page, and so we end up with a 1 over x coming out of that. If you want to leave it written like that, you can, but most people go ahead and write it this way because it looks just a little bit neater. Okay, so let me copy that down here. Now I'm going to get all into this notion of making these formulas easy to find, I guess. So, yay. All right, I might move that a little bit over here. Okay, so cool. So the next formula that we need here is actually going to be showing that the derivative of b to the x is going to be b to the x times ln b. Now, on the previous page, we had gone ahead and made some progress on this because we knew that that meant we were going to rewrite the b to the x as e to the x ln b, right? And then you got to remember that the derivative of e to the something is e to that thing. But then you have to use the chain rule and take the derivative of x ln b. Remembering ln b is just some constant, we're taking the derivative of x to get 1, and we get just this ln b floating out there. Once you've got that, though, you have to remember that e to the x ln b is really b to the x. And so that's where that formula comes from. All right. So copy, paste that right there, and put a little rectangle around it. And yeah, I think that looks good. All right. So using all those new rules that we just got there, we're going to do a few problems where we find the derivative of stuff. So this first one here, we're taking a derivative of ln of x cubed plus 3x minus 4. Okay. So the first thing you got to spot is that this is a chain rule problem. There's an ln on the outside function, and then the inside is this polynomial. But so we will take our L prime of x, and now we have to say the derivative of log is 1 over whatever was inside the log. So we're going to put the x cubed plus 3x minus 4 in the denominator of a fraction like that. But then the chain rule says that we have to take the derivative of that stuff we put down there. And so we'll have 3x squared plus 3. So for this, you can just write it as 3x squared plus 3 divide x cubed plus 3x minus 4. Now, if it should happen to be the case on one of these that factoring something like the 3 out here means you could cancel something, go ahead and do that. But I don't really see that that's going to get us any benefit here. Likewise, if this were asking us to identify where something is increasing and decreasing, then we could set that numerator equal to 0. And so it would be super convenient to have that factored. But again, this one just asks us to take the derivative and nothing more. So, all right, here we go. This is one that asks us to figure out where something's increasing and decreasing, and it's got a log base 2 in it. So when we come along here and we say our f prime of x, we have to first of all say, okay, log base 2 of something, actually, I'm going to show you a trick first. This is something that you should learn to do as somebody who uses mathematics. Always look at whatever you're given and see, did they write something that was needlessly complicated? For example, here, I have a power in there. You may not think of it as a power, but log base 2 of the square root of x is really log base 2 of x squared. I said square root of x. Square root of x squared plus 2 is really the log base 2 of x squared plus 2 to the 1/2 power. And the reason that is important is that we have a nice property of logarithms, and this goes for all logarithms, that if you have a power that's the power of the whole thing there, that you can pull that out. Might be worthwhile for me to write down here to the side log base b of x to the n equals n log base b of x. Likewise, log base b of x times y is the log base b of x plus the log base b of y. And the log base b of x over y is the log base b of x minus the log base b of y. So I should put little rectangles around those so that we can spot them easier. Now that was weird. So once we've got those in mind, then we know about pulling that 1/2 out there. And so when you want to find f prime of x, you'll have to say, what is the derivative of the log base 2 of something? Well, from a previous page, we found out it was 1 over that thing, then times the ln of the base, in this case, base 2. Then what? Then you have to remember the chain rule. I seem to be hammering on this chain rule pretty hard, don't I? But you have to remember this chain rule to take the derivative of the x squared plus 2. Now, fortunately, that's something that's not too bad. You get just that 2x. And then you can spot that the 2 and the 1/2 cancel out. And this turns into x divided by the x squared plus 2, and then the log 2, okay? If in high school your teacher told you to distribute everything possible, resist that temptation here, because it doesn't actually benefit us to distribute the log 2 across that x squared plus 2. Okay, just leave it as is. All right. Now, what were we doing with this? Well, the thing that we were doing was taking the derivative so that we could set this equal to 0 and solve. If you have something that's set equal to 0 and it's a fraction, that means that the top had to be what was 0. So the only place that this is 0 is at x equals 0. We should probably also check, is there some place that makes the denominator 0? And because it's got an x squared plus 2, it's always going to be greater than or equal to 2. So we don't actually have to worry about that in this particular problem. So once we have identified that, that x equals 0 is the only breaking point for it, then you identify a couple of numbers, something that's a little bit less, and something that's a little bit more. And ironically, I wrote the more one when I said less, but all right. So now you'll have to check and see that f prime of -1 is going to be equal to, and it would be -1 over, -1 squared is 1, so you end up with a 3 ln2. So this is giving you something that's negative, so it's decreasing there. And then on the other part, the f prime of +1, you end up with 1 over 3 ln2, and that is positive. So you've got something that is decreasing then increasing. So decreasing and then increasing. So for the decreasing, it goes forever to the left, and then at 0 it changes and starts to increase, and it increases from 0 to infinity. Okay. If you take a look at a graph of that, you'll see that that displayed there kind of nicely. So, all right. So here is a problem where we use exponentials a lot. If you take a look in your textbook, you'll notice that you'll see this formula appear a lot. And actually for radioactive decay, they tend to use a K. Actually, what they tend to do is to write -K because they want to emphasize that this is radioactive decay. If you have something that's exponential growth for a population, it will end up being a P equals P naught e to the RT, and we think of the R as being positive there. There's also something where you're talking about continuously compounded interest, and it's all the same kind of formula for it, right? But this setup here, we say there was a mummy found in the Gobi Desert wearing woven cloth. It's actually something kind of a neat find from a few years ago, where the cloth looks like from the weave, it probably came from the eastern steppes, and I'm sorry, the western steppes instead of the eastern steppes. So there was like nomads living around the Gobi Desert and stuff, and it's kind of neat, you know. In any case, though, when you take that cloth, I think it was some sort of wool, and you compare it to similar cloth using a Geiger counter, you can identify that the carbon that's in it only has 63.1% as much carbon-14 as what you see in modern cloth from similar sources. So we're going to try to find out how old that cloth is. One of the things we have to be able to do is to figure out what's going on with carbon-14. And with carbon-14, it has a half-life of 5,730 years. Okay, you can just look that up somewhere if you need to. But what that means is if you start out with a certain amount of carbon-14 in something, after 5,730 years, there will be half that much from radioactive decay. So that means that if you take A of 5730, that you can plug into the formula and have the A naught e to the -k times 5730, but that you could also say that you have 0.5 times A naught because it's half as much. So then if you divide out the A naught, then you have an equation to solve here that's e to the -5730k is equal to 0.5. And if you take natural logs on both sides, you end up with this. And so the k that we're talking about is going to be the negative of ln 0.5 divided by 5730. Personally, I don't like the whole setup trying to force the k to be positive and stuff. So yeah. Well, in any case, if you're approximating that, you're going to get about 0.000121. And you can be more exact than that if you want to, okay? But we are going to make use of that as we go along here. And we're going to estimate how old the cloth is. Because we know that the A of t being A naught e to the minus kt with the value of k that we now know, but I'm not going to plug it in, okay? We know that however long this has been aging, we ended up with 0.631 A naught here, okay? And that means if you cancel out the A naught just like before, you can have the e to the minus kt equals 0.631. And then taking natural logarithms, you have minus kt equals natural log 0.631. And t is equal to natural log of 0.631 divided by this negative k. And if you've got a calculator at hand, which I do, you can get a quick estimate of that, negative 0.000121. Bear in mind, you have to count your zeros, because if you mess up on those zeros, you end up getting the number being the wrong order of magnitude even. I'm getting out of that 3,805.3 blah, blah, blah. So about this many years. Now, of course, if you look back through this problem, everywhere that we've done stuff, we've only used 3 significant digits. So it probably doesn't make any sense to be too exact. We'd probably say 3,810 years. For scientists who actually know what they're doing, as opposed to, me, there's actually some limitations about your carbon-14 dating process that suggests that you really shouldn't end up trusting it even that much, that the value of k that we're talking about, copy, paste, you're really not going to be able to get these estimates any closer than about 50 years off. So that means that our estimate that we've written down here, probably we should just say 3,800 years. That's about as close as we're going to estimate it. So, all right. Okay, so then we're going to take a look here at this trick. Is this the last thing? Yeah, this is the last thing in here. This trick here is referred to as logarithmic differentiation. And it is a trick that allows us to differentiate some things where it looks like we're going to have to use really hellish quotient rule stuff and chain rule stuff and make it relatively nice, okay? Now, if you already have a logarithm in it, then you just apply the rule. But we're going to insert a logarithm in order to make this turn out nicer. So if I took the logarithm of y and then took the logarithm of all that jazz on the other side, 1 minus 10x and the square root of x squared plus 2, then we need to remember the logarithm rule from a previous page that said when you divide things, the logarithm turns into subtraction. So logarithm of the x to the fifth minus the logarithm of 1 minus 10x minus the logarithm of the square root of x squared plus 2. Okay. But before we launch right into this, we also ought to note that our power rule allows us to do that. The 1 minus 10x we can't do anything about, but the square root we can do that with. All right. So now when we differentiate both sides, there's a little bit of trickery here in that you're differentiating log y with respect to x. You will get 1 over y ln, sorry, not ln, times dy dx. So we differentiated a logarithm, and so we got 1 over whatever was inside the logarithm. And then we had to apply the chain rule and take the derivative of what was inside, and that's why the dy dx appears. Okay. So then this is equal to, we're differentiating the other stuff, 5 times 1 over x, and then minus 1 over 1 minus 10x, so it's 1 over there, and then times the minus 10. And then minus 1/2 of, we take the derivative of the logarithm, so 1 over the x squared plus 2. And then the chain rule says we have to take the derivative of the x squared plus 2, and we put the 2x on the outside there, okay? Now, everything that you can simplify, you simplify, and 5 over x plus 10 over 1 minus 10x. Hope y'all spotted the minuses canceling there. And then minus the 2's canceled. And so you end up with minus x over x squared plus 2. Okay. Now we're almost done. It's all we have to do now is to multiply both sides by the y in order to get the dy dx by itself. So dy dx equals 5 over x plus 10 over 1 minus 10x minus x over x squared plus 2. And if you want to go ahead and pull things together over a least common denominator there, you can. I don't see that there's really a whole heck of a lot of use to it here. But now we need to multiply by the y. And rather than just put the y itself there, I'm going to go back to the original y that we had and write the 1 minus 10x here, and square root x squared plus 2, and then divide all that and have an x to the fifth. The reason I go ahead and do that is that I might, on another problem, have to actually plug in x values in order to check the concavity or increasing or decreasing on all these functions. So, all right, that should get us. And like I say, the differentiation on these, it's new rules, but it's not like whole new ways of thinking or anything. All right. Okay. I'll see you all in class.